Before I made a video on the superposition property for second degree or higher linear recurrence relations. And so what I'm going to do in this video is show a modified version of the superposition property that's for systems of recurrence relations. Except now they're going to be systems and they're all going to be first order. So it's going to look really familiar. You also may have seen a superposition property that looks almost identical to this if you've studied systems of differential equations. So for the homogeneous case, we have this type of recurrence relation is what we're looking at right now. It's very general. A could be an m by m matrix, so you could have m equations and m unknown functions. And so if you look at what this equation tells you, it's just saying if you take your solution fn, if you iterate it once, that's the same as doing the matrix product A times fn. So what I want to show with the superposition property is that if I know any two solutions to this equation, then any linear combination of them is also a solution to this equation. So in order to show that, I'll need to show that by multiplying any linear combination of two solutions by A, that's the same as iterating it. So here it goes. So let's let f1 and f2 be solutions to star this equation here. Then what I'm going to do first is I'm going to kind of start with the right hand side. So we take a linear combination of f1 and f2 and we matrix multiply with A. And so it's important to remember here what these operations mean. This is a matrix multiplication. This is a scalar multiplication between a scalar and a vector. This is a vector addition. But luckily, these and kind of the reason that these are given the same symbols and lack of symbol here as the regular arithmetic operations is because they do have a lot of the same properties. You do have to be a little careful because you know multiplication is not commutative with matrices, but we don't have to deal with any of that here. We do have a distributive property, so we can distribute this times this plus this times this, and we also can commute these constants C1 and C2 out to the outside here. And so now A times F1, since F1 is a solution to star, A times F1 is just F1 like iterated once. And same with F2 here. And so what we get is this is the iterated version of what we put in. C1 F1n plus C2 F2n. So in the end, as it turns out, any linear combination C1 times this plus C2 times this is also a solution to star. Okay, now that we got that over with, let's look at the non-homogeneous case. So to form the non-homogeneous version of this type of equation, all I'll do is add on this extra known function over here. I'll call it phi of n, 5n, however you pronounce that, phi, phi, pho, fum. So now let's say we know the homogeneous solution. In other words, the solution to star, which is the equation I have up here, the one without phi. And let's say I also know a particular solution, a solution to this equation here. So this star is the homogeneous one, this is the non-homogeneous one. So what I want to show here is that if I add these two together add any particular solution to the homogeneous solution, that's also a solution to this non-homogeneous equation. And this just is to make it easier to find solutions later down the road. So it's kind of the same technique. You just plug in what you're interested in, the sum of these two functions, plug that into the right hand side here, do a little bit of work with it. Again, we have the distributive property here going on with matrices. And then what we have is A times F, the homogeneous solution. That's just Fn plus 1, the homogeneous. And then over here, we have A times the particular solution plus this thing. And so we can kind of think of this all as one unit here. This can be replaced with this. So we replace that with Fn plus 1, the particular solution. And so what we got out in the end was just an iterated version of what we put in, meaning that this is a solution to the equation here. Okay, now that we got that over with, let's look at what that can do for us. So here's a fact that I won't prove. The general solution to an m by m homogeneous system is an m-dimensional vector space. So what that means is if we have an equation like this, and A is this, an m by m matrix, then the solution just looks like this. It's just a linear combination of m different solution functions that are each particular solutions, and they're all linearly independent. So if we want to find the solution, in other words, this combined with the superposition property lets us say all we have to do if we want to find the general solution is find two, like for example if it's a 2 by 2 system, all you have to do is find two different solutions that are linearly independent, and then the general solution is just a linear combination of them. Okay, so that's pretty useful, or it will be useful when we try to find the when we try to solve this type of equation in general. And that's kind of the goal right now, is to be able to solve this type of equation in general. Alright, so let's look at something I showed in the last video. We said if we look at this linear recurrence relation here, it's just a single equation where A is non-zero. We found out that we could actually mess with this a little bit and get it into the form of one of these, to like a 2 by 2 system. The g of n function is just the f of n iterated once. And then because we knew what this was to start with, since we know how to solve this recurrence relation, then we could find the solution to this 2 by 2 system, and we found that it was this. The vector containing fn-gn, also known as fn, the vector, is just equal to this, a scalar multiple of this vector and this thing to the n, and this one to the n. So so what we can do is we can kind of try to, like, well, we're trying to generalize this. We're trying to solve in this general equation up here. So